At 3,600 revolutions per minute, a microscopic structural flaw will tear a 5-ton industrial turbine apart. This violent shudder shatters steel housings and halts production lines, triggering millions of dollars in mechanical damages and lost revenue. This destruction stems from a conflict between two invisible lines. The fixed central line is the rotational axis, the path the machine forces the object to spin around. The secondary, offset line is the principal inertia axis, the natural center of mass where the object actually wants to spin. As the rotor gains speed, these two axes fight each other in three-dimensional space. The physical vibration we measure is simply the byproduct of that geometric struggle. Because engineers cannot look through solid steel during operation, they must deduce this internal misalignment entirely from the vibrations vibrating through the external bearings. Decoding these signals requires recognizing three distinct evolutionary stages of spatial misalignment. The first stage is static unbalance. The principal inertia axis remains parallel to the rotational axis, but shifts to one side. Consequently, vibration amplitude is identical at both bearings, and phase angles are exactly the same, pushing both ends simultaneously. This parallel alignment acts as a uniform centrifugal force, pulling the entire rotor outward in a single consistent direction. With couple unbalance, the principal inertia axis is tilted, intersecting the rotational axis in an X shape. Once spinning, this tilt generates identical vibration amplitudes at both bearings, but phase angles are exactly 180 degrees apart, creating a violent seesaw effect. While these intersecting axes hide their flaws during static tests, they weaponize opposing directional forces as soon as high-speed rotation begins. Real-world machinery faces dynamic unbalance, a combination of static and couple errors. The principal inertia axis is skewed, completely missing the center of gravity. This chaos creates asymmetrical vibration amplitudes, and phase angles lose all synchronization, differing by random amounts. This compounded error is the standard state of almost all failing machinery in modern industrial settings. To fix this, engineers treat the dynamic skew as the sum of its parts. By mathematically separating the parallel offset from the angular tilt, they deconstruct the chaotic movement back into its base static and couple components. With the complexity broken down, an engineer only needs to cross-reference two external sensor readings, amplitude equality and phase synchronization, to instantly deduce the hidden internal geometry. This diagnostic matrix connects those symptoms to their geometric cause. If amplitudes are equal and phases are in sync, it's static. If amplitudes are equal but phases are 180 degrees apart, it's a couple. If everything is unequal and out of sync, it is dynamic. Identifying the specific type of unbalance provides the exact coordinates needed to add or remove weight with precision. By adding engineered counterweights, technicians use mass to pull the principal inertia axis back toward the center until it merges with the rotational axis. Mechanical balance is more than just stopping a shake. It is the process of using physics to align